Okay, so I assume the homework assignment was trivial for everybody?
No. You got some jokes today.
Yeah, exactly. A lot of people didn't show up.
We should
Why?
have an attendance quiz. Attendance quiz.
Katie's not here again. Does Katie have diarrhea again?
Where?
Hmm?
Yeah, where
Does
is
Katie have diarrhea
everybody?
again?
Does she still have diarrhea?
She seemed fine yesterday.
Did you go to the meeting?
Yeah.
I couldn't make it.
Where's everybody else?
I don't know.
Where's Joel? Is Joel in this?
It was like what? 6
He is, but he
hours?
takes it online because he's in another class at the same time.
Fair.
Oh.
8 people.
Nah, he's stupid though.
A helmet.
I'm missing him.
I voted.
Alex isn't been here.
I'm voting attendance
How many
quiz.
people are actually in this class?
Yeah.
Double of what's here.
Seems pretty empty.
All right, so let's look at this assignment. What class is this? Yeah, Towers of Hanoi, right?
Yep.
All right, so I already have it recording. Yeah, we're good. So I have the calling this one student stupid on this as well as the explosive diarrhea. I've just reiterated for the.
Gotta make sure they know.
All right, so as it stands right now, what does our driver do? It creates a tower object and then adds some disks to that tower object and then displays the tower. Then we remove some disks, kind of proving that we can do that, right?
Mm-hmm.
All right, so that's what the guy currently does. Now for our assignment, you were supposed to create some sort of prompt, right? We were supposed to ask the user what they want to do. Give me the source tower, give me the destination tower. So for right now, we're going to do all this in main. Then we're going to move it into an object. So I'll just get rid of all this stuff. I'll go ahead and create our a tower array called the towers. And this guy is going to be equal to,
That's really funny. That's exactly what I
well, it's
think.
because I taught you how to program.
Literally, well, you capitalized the T, I did.
So
I tried.
if we
So you created yours like that. Could you just do it? Or, well,
Yeah, we did.
Because I did it.
You could have done it this way. Tower array, the towers, 2
Yeah, okay.
is equal to new tower array 3, like this,
Yeah.
right? And then you could say the towers 2 at bucket 0 is equal to a new tower.
Okay. Cool.
The towers 2 at bucket 1 is equal to new tower.
You just have it all in one.
what we tried to do was create
Okay.
create new towers outside and then put it in an array.
Which is fine.
We tried it inside of the curly braces too.
We must have messed something small up.
Yeah, I think we just missed the parentheses.
Well, I mean, you can create the towers beforehand. You can say tower T1 is equal to new tower.
Yeah, that's what you sent us and told us to do afterwards.
Which is fine.
Yeah.
Actually, it's not what I sent you, but you must have misread my message, but that's okay.
Works out.
And then you could say T1, T2, T3. Like that.
Okay.
So there's 3 different ways of accomplishing the exact same thing. Okay. At the end of the day, what do we have? We have
An array with 3. Or
an array with 3 towers in it.
Yeah.
All right, so that's what we have there. We have an array called the towers that actually has 3 real towers in it. Okay, so now to answer your question, show you a graphical version of this. How does this work? Well, we have the towers. Okay, now what kind of value is the towers?
array.
So if I do system.out.println the towers, what will print?
Memory address.
A memory address of what?
For the location of the array of towers.
Location of the array. So this is the memory address associated with a tower array. So here's that. So let's just say that tower array lived at memory address 10. Just keep my numbers simple since I'm going to have to make some double pointers here. All right. You going to cry?
No, I might pass out though.
That'll be awesome. So now up here at memory address 10, except these, we know that memory addresses are always green. We actually have buckets of our array. And these buckets are, the contents are always, well, they're always blue, right? Yeah.
Can we make them purple here?
Nope.
Blue.
Oh, well, the values are always blue. That's our schema. All right, so this guy is said to point to the beginning of the array. Now, this array is built to hold 3 towers. So this is a normal array, just like any other kind of array. Here's the memory address. What is a tower? A tower is a pointer. So this might be memory address 74. This might be memory address 92. And this might be memory address 17. All right. How big is a memory address in Java? Well, we can make a guess. If it's the 32-bit version of Java, the size of a memory address is 32 bits. If it's a 64-bit version of Java, the size of a memory address would be 64 bits or 8 bytes. So if we say it's 8 bytes, this is memory address 10, this is memory address 18, and this is memory address 26. So this would no longer be 17 because those would bridge. So we're going to make this guy 29. All right, so our array, bucket 0 of our array is the towers plus 0 times size of memory address, which takes us to the towers, which is 10 plus 0 times 8 for bytes, which is just 10. That's where bucket 0 lives. Zero, 1, 2. Bucket 1 will live at the towers plus 1 times size of memory address, which is 10 plus 1 times 8, which is 18. Memory address 18 is where bucket 1 is. And the value there is a memory address. Okay, why is that? Well, if I do system.out.println towers at bucket 1, what's going to print out? A memory address, the memory address for a tower. Not a tower array, an actual tower. So this guy is a pointer to an array which contains 3 pointers. And these guys actually point, well, let's just do it this way. So memory address, I don't know why I did that, but whatever. So at memory address 74, we have a tower. At memory address 92, we have a tower. At memory address 26, we have a tower. 29, thank you. Memory address 29, we have a tower. So this guy points to this guy points to this guy points to this guy. So these are double pointers. This is a pointer to a pointer, which points to an actual tower. Pointception. Okay. Pretty funny that you can have that complex of pointers in a language that doesn't support pointers. Remember when we talked about Java doesn't support pointers? Yeah, there's a lot of pointers going on here for something that shouldn't exist. All right, so the actual tower itself lives at the memory address. So the tower that's stored in bucket 0 of our array is actually located at the memory address we have stored in bucket 0, which is over here, and that's where the tower is. That makes sense? So the towers is the memory address of the array. The towers at bucket 1 is the memory address of the tower at bucket 1 in that array. And that tower has a add disk method. Or tower 0 has an add disk method. Or tower 2 has an add disk method. Because now you're talking directly to the towers. Make sense? Make sense how these pointers are working? So right off the bat, we're going to create our tower array. Then we're going to go ahead and create a scanner. Input is equal to new scanner system.in for reading crap in. And we'll just do a infinite loop here for right now. Need to import java.util scanner. All right, each time through our loop, we want to ask a question. We want to ask what the source, and we want to ask destination. So what's the source tower? What's the destination tower? Make sense? Okay, and what we can do though is every time through the loop, we probably want to show them the current state of each of our towers. We already have a display method, right? So we have empty tower, and we have the one that goes through and shows us the disks. I mentioned at the end of class last time that maybe for mental sake, you might want to put some dividers or something like that in here.
What's the point of creating a show if we have it automatically display it then?
Huh?
You wanted us to include a show method. Or
Yeah, the new state of
show.
everything. Yeah, so
If we're going to make it automatic.
yeah, each tower knows how to display itself.
Okay.
Each individual
Okay.
tower knows how to display itself. Okay, and I asked you to make a show method. In our model here, we'd make it out here driver, right?
Mm-hmm.
So the show method is going to be static void show, take no parameters. And what this guy is going to do is it's going to say, we've done for each loops, right?
No.
Ever done a for each loop? Oh, I'll show you a for each loop in a minute. So for int I is equal to 0, I is less than, actually I need to pass this guy a tower array because of the way we're doing this. The towers.length, I++, and we're going to say the towers at bucket I dot display. And if we want, we can put an extra little space in there or something like that, just to kick it down an extra line. All right, so if we want to test that real quick, I can go ahead and say,
You're gonna have an error because there's nothing there.
I won't get an error. Driver.show the towers, and we'll just have 3 empty towers. Right? Because my display method for tower detects to see if it's empty. And it says empty tower. Make sense? But we do need to start off a tower with some disks on it. And what I say, start off with 3 disks. Okay? And we want we got to make it legal. So out here we'll take the towers at bucket 0 dot add disk, and it's supposed to, this guy takes in a new disk and a size. So we want to do 3, then 2, then 1. So we'll do a size 3 first, then size 2, then 1, since we're putting them on as a stack. All right, so now we've created a default. That far left tower, tower 0, is going to have 3 disks on it. So now when we run this, we'll see that our first tower is not empty. First tower shows 1, 2, 3. And the other towers are both empty right now. That make sense? Now, what we might want to do is we might want to go ahead and give indexes for these in our show, just so we have something to reference. So we might say system.out.println tower index I.
I think for your example, you just had it as part of the asterisk.
That's fine.
Yeah.
It doesn't matter. Whatever. So this is tower index 0, this is tower index 1, this is tower index 2. All right, makes sense? All right, so that's what our show method will do. So we're going to put that inside of a while loop. So while true, we're going to just keep letting them do stuff. So we'll go ahead and we'll show them the current state of the system. Then we're going to say, we'll assume they give us good input. So we'll say int source is equal to input dot next int. And we're going to prompt them first, system.out.print, enter source tower index. Then we'll read it in. Then we'll have them enter destination tower index. And have them enter that in. Okay, now if you go back to tower, you see we already have an add disk, right? But add disk returns a Boolean, whether or not the disk was successfully added or not. So the first thing we need to do is we need to remove the disk from our source. Try to add it to our destination. If destination spits back, if add disk for our destination spits back a false, that means it was not added. In which case we need to then push it back onto our original. So we're going to go ahead and say disk, we'll call this D2 move. Okay. I thought that was an inside joke, or maybe an outside joke. And then nobody got it. Still nobody? Okay, good. Good Christians. Watch the final episode of season 1 of Silicon Valley.
I need to get my...
You won't stop laughing, ever. You'll never stop laughing, actually. I just stopped about 10 minutes ago, and I saw it several months ago. Okay, so disk D2 move is going to be the towers. Don't say anything. It's going to be the towers at bucket source. So we'll assume they enter an illegal source and a legal destination. Did you just get it too? But you just think it's funny. And then it means
Everyone else.
I don't think. How many people actually here actually get it? Just one?
We didn't hear it.
Huh? You didn't hear it?
No.
Here, I'll do the where am I at here? Oh, this. So I named my variable here. So D2F would be a variable name that should connect the dots. So maybe after class when we're not
I got it.
when we're not on recording, I'll
What about D to H though?
T2O. All right. After class, I might be willing to share this with you since it's not my material. Okay, so in any case, the disk that we're going to move is going to be the one from tower source dot remove disk. All right. Then we're going to say if the towers at bucket dest dot add disk D2 move, if that returns a false, so if this is not true, then what are we going to do? We're going to say the towers at bucket source dot add disk D2 move, because it did not. We tried to add it to our destination tower right here, and if it returned a false, that means it was not. It broke the rules. It wasn't because of the current state of that tower. We couldn't add it to that tower. So then we have the responsibility of putting it back onto our source tower.
And we want to print out fail.
Yeah, that's fine. So we can say system.out.println illegal move, just to let them know that something bad happened. All right, that makes sense? So that should be the whole homework assignment. So this should allow us to just keep moving disks around. So,
Why did it take us so much longer?
well, didn't I say in the text message last night that dummies?
Yeah, for sure.
Well, we haven't tested mine yet, so we're not sure it works. All right, so we have our tower index 0, our tower index 1, our tower index 2. Enter the source tower index, so we're going to remove from tower 0. Okay. And again, we're assuming we have legal source and destination towers. The one weakness we have right now is technically we can try to remove from tower 1, and there isn't a disk there, so we get a null value. Okay, so I'll go ahead and remove from tower 0, and let's put it onto tower 1. Now it's showing us.
That's exactly what mine is.
You need a, what it was is you have to,
So what happened?
you have to get the size and stuff.
So I removed it here,
But when you remove it,
and then now this is tower index 1,
yes.
right?
It's sending all 3.
Okay, why is it sending all 3?
You have to grab
Because you had
the
to-
top.
What we did was we grabbed the top.
Top
Did we write remove disk
Yeah.
poorly?
No.
Well, here's remove disk that returns a disk.
Yes.
So the node to return is going to be the top. If top is not equal to null,
But you had to create a new disk. I don't know, we figured this out. You had to create a new disk that is the current dot size. Or get size.
Yeah, we made it temporary.
no, you should have to. Well, let me just look at our code here. So this is the disk we're going to return. This is the top of this particular tower. So if, after we've set the disk we're going to return, if top is not equal to null, then we're going to set top equal to next disk. And then we'll return the node that we're going to return. Right? Okay. So the question is, and actually this is the issue. So we are returning this node, this disk. And this disk, this guy right here, currently is still linked to the disk after him. Right? He still knows about the disk after him. So follow this with me. So we're going to return the top of the stack. So if we look back at our running program here, when I say take source is 0, destination is 1, I'm going to remove that disk from the stack. Now, as of right now, this disk is linked to this disk is linked to this disk, right? So when I remove this from here, and I pop it off, and then I push it onto here, we saw it was legal. But this guy showed all the disks. Why? Because this guy is still linked to this guy. Remember how I recommended that you always explicitly disconnect everything? So I tested you last class and nobody passed the test. So if it's not equal to null, before we do anything else, we want to say node to return dot set next disk to null. We actually need to disconnect it from this linked list. That make sense? And it actually only breaks the very first time when we put something on, because when we add a disk to the empty list, we just set top equal to that disk. We don't check to see if that guy's still connected to somebody else. Okay, so the top of tower 1 was that disk 1, which was still linked to disk 2, which was still linked to disk 3 from tower 0. So when we remove a disk, we need to make sure that we explicitly remove that disk. Disconnect it from the stack it's leaving. Make sense? So remember when I harped on I like to always explicitly disconnect stuff? Here would be a good example why. So now this guy should work. So we'll go to 0 to 1. So we removed from tower 0, put on to tower 1. Go to 1 to 2. Tower 1's now empty. Tower 2 has that guy. Let's do 0 to 2, which should be illegal. 0 to 2. Get an illegal move. So things are still set up the way they were before. So on and so forth. 0 to 1. So now we have something in every single one of our towers. Make sense? All right, so that should solve the homework.
Should you upload that to GitHub before you make any more changes?
Wasn't that easy?
Look that way.
I'm glad you guys were challenged. That's what I look for. I don't want to give you easy assignments you can just breeze right through. You're not getting any experience then. That's just busy work, right? So you appreciate the night you had last night. It was my gift to you.
Yeah, thanks.
There's an advantage to some of the easier stuff, though. It builds confidence.
Really?
What's that?
What's confidence? You guys are students. You're not supposed to be confident. You're supposed to feel like you're a little bit less dumb than you were a week ago. It's like, okay, progress. All right, show System Explorer. Okay. All right, so we're going to do a pound 590. That's got to be freezing in some world. All right, so now it should be,
Bang.
huh?
Bang.
Oh, yeah, bang. Yeah, I always want to call that pounding because, I don't know, that's freezing. D2F. All right, so it should be up on GitHub now. All right, questions about that? Oh, actually, it's not going to be on GitHub.
You don't have
I didn't commit. No, I do. Git
That's not it.
commit dash P or dash M. Homework solution.
But you don't have a.
I do. I put it up there last time.
Oh yeah.
Now it should be up there. I didn't commit the changes.
Yep.
All right. So, questions about this? So now what we want to do is we want to move this into a game object. So our main isn't this large chunk of stuff. So I'm going to create a new class. Actually, before I do that, let me just quickly, whatever. I was going to create my quick script, but not a big deal. I'll just do 3 commands. So let's call this guy game. All right, we're going to move a lot of the things we just did out in main into game. So game is going to have a public constructor. Public, blah, blah, blah. So we have public game. This guy's going to take in no parameters, and he's going to do the initial setup for Towers of Hanoi. All right, so we're going to take, where am I at here? Driver. I'll just drag all this stuff into the constructor for right now, and then we'll move it around inside a game. All right, so we're going to need to have a private variable up top. That's going to be our tower array. Part of the constructor for game is going to be to fill that first tower up with some disks. All right, we're going to move this stuff probably into a method called play. Something like that. All right, then we need to go ahead and grab our show method, because our Other guy is utilizing that. And our show method is no longer going to be static. It's now going to be a private method because we don't want them to be able to access it outside of this class. So it'll be a show method. It's going to, and it also doesn't need to take in the array of towers because it already knows about the array of towers. So we'll say this dot towers dot length, and then this dot the towers, so on and so forth. We'll access our instance variable called the towers up here. Make sense? So we just moved everything we had in main out here into game. Notice the way we're currently calling show is driver.show, but show is no longer a class method. It's now an instance method. We removed the static. So we call it by saying this.show. Make sense? All right, so now out here in main, we could just say game TOH is equal to a new game, and then TOH.play. And we'll get the exact same experience we just had. 0 to 1, moving the stuff around, blah, blah, blah. So doesn't this look a lot cleaner out here? This goes back, way back to when we talked about the difference between procedural and object-oriented languages. The procedural version of our telephone was the pile of wires. That is what we used to see out here in main, all the details. And now the object-oriented version of our telephone is something nice and clean like this, all contained inside of our game object. And the game object and all the other objects have our details in it, under the hood. Why can't you just keep up?
Because I was grabbing all your code.
Before I change it. You could roll back to old changes.
I know, but I want to stay current.
All right. So, makes sense where we're at right now? So now we need to take our game a little bit further, and that is we need to be able to know whether or not there was a win. How do we know that somebody won?
If the third tower is 1, 2, 3. No.
There's 3 things on the third tower, right? We're already self-policing our moves, correct? Already self-policing our moves. So we just need to look at the third tower to see if there's, assuming we're keeping our game to a maximum of 3 towers. If you saw like the Towers of Hanoi examples, you could actually expand that to have, you know, a zillion different towers if you want. But for us, let's just keep it at 3 towers for our example here. So really to check to see if there was a winner is to just look at tower 3, or tower at bucket 2 in this case, and say, does that guy have the maximum number of towers, right? Which is 3. Well, let's look at our tower. Does this guy have the ability to tell us how many disks are on it? It doesn't right now. So we can add that feature to our tower. We can say private int numDisks. In our constructor, we'll say this dot numDisks is equal to 0. And every single time we successfully add a disk, we'll increment numDisks. Every single time we remove a disk, we'll decrement numDisks. So at all times, every tower should be able to keep track of the number of disks that it currently has. So remove disk. We'll do this dot numDisks minus minus. Okay, now we probably want to do something in here because right now we allow them to remove null. Okay, so we probably want to tighten this up a little bit. So we're going to get into a variable node to return is equal to top. If the top is not equal to null, we're going to do our disconnect. If it is equal to null, what do we want to do? Probably just return null. Something like that. Make sense? will never get down to this line. So we don't want to decrement when there was nothing there. We don't want a tower to go from 0 disks to -1 disks because we returned null. We returned a disk, what was supposed to be a disk, from the empty tower. Make sense? All right, so we're only going to decrement the number of disks in that case. And if we wanted to, we can actually just take these 2 lines and put it at the bottom of the if clause here. They both are functionally identical. So if this is true, do all this stuff. Else, just do this. Okay, so now our remove disk is a little bit cleaner. So that's when we do this.numDisks minus minus. But whenever we add a disk, where if it's the empty tower, we just trivially add a disk. So I need to make sure that I say numDisks plus plus here. If we do allow a disk to actually get added, we want to say numDisks plus plus here. In the case where we return false, we didn't actually add a disk. Okay, so if we either trivial add a disk or link the new disk into the stack, we'll increment the number of disks. Otherwise, we just return false. We could not add this. Okay, so when we remove the disk from one tower, its count will go down. If we happen to try to put it onto another tower and fail, and then we end up putting it back onto the original tower, its count will just go right back up to where it was. Make sense? So every tower will maintain its count itself based on when we take something off and when we put something on. So in our case of an illegal move, when we take something off, its count just went down. We try to put it on another tower but fail because we broke the rules. Now we can put it back onto the original tower, which we know it'll meet the rules for that. We don't need to check because it used to be on that tower. Then the count will go back up by 1 because we just added it. All right, so now towers are keeping track of their number of disks. So we just need to add a getter for that. And we're going to do this for numDisks, just get numDisks. Okay, so now a tower is able to give us the number of disks. Now back in game, after we make every single move, before we spin back up, we're going to say if this dot the towers at bucket 2, we know that's the last legal bucket, or we could say this dot the towers dot length minus 1. If that guy dot get numDisks is equal to 3, then we're going to break. That'll get us out of this infinite loop. And we'll say system.out.println winner. And then maybe we do one more show. This dot show. So this is our check for winner. Right here. If the last tower in our array of towers has a number of disks equal to 3, break out of this infinite loop. We don't need to allow them to move stuff anymore. We'll say they are the winner, and then we'll show them the final state of the game. So let's go ahead and run this real quick. So I need to go from 0 to, 2? It's not the easiest playing board. Then 0 to 1. Then 2 to 1. Then 0 to 2. Then 1 to 0. Then 1 to 2. Then 0 to 2. We should have our winner. Here's tower 0, here's tower 1, and there's tower 2 with all of our disks on it. And it's no longer asking me for inputs. Make sense? So that's fully functional Towers of Hanoi game. With all the graphical splendor you could ever want.
But it doesn't say you won.
Yeah, it does.
Yeah,
Up the top.
it's at the top. It prints it out first.
Winner. You want me to print it out last? There. Now to print out last. I'll beat the game again with my savantness. 1, 2, 1, 0, 2, 1, 0, 1, 2, 0, 2. All right, so there's Towers of Hanoi. Isn't that interesting how the fully functional game was just a hop, skip, and a jump from what you did for your homework assignment? A couple little changes. And look what our main method looks like. Very entertaining.
When I was doing some research online, like a bunch of people were using recursion for Towers of Hanoi.
Okay.
Do you think that this way is better?
Well, I mean,
A lot of people were
it's not
using
so much
built-in
better.
stack.
Recursion is implemented in terms of a stack and a loop.
Yeah.
So we're using stacks. I mean, I guess I'm trying to think how do they use recursion?
I don't know.
I
You
think
could do a quick
if
search. I didn't
they were-
delve too deeply into it.
From what I saw, they're using recursion with the built-in stack method. I think that made it possible.
Well, we could use the built-in stack method and pull this off pretty easily. But I don't really see the point in using the built-in stack method typically, because we can just write our own for what we need.
Yeah.
I mean, if we want to change tower, I mean, for us, adding a disk, we wanted to return a Boolean. I don't know if the built-in stack one, let me just look at this real quick, stack blah java.util blah dot add. Oh, it does return a Boolean. But we would need to override that method anyways. Push. Yeah, in this case, I don't think it would help us that much. We do have something called generics, where we can say we want a stack of disks. And this is going to be a new stack of disks. So now when we say blah dot push, it's taking a disk as a parameter, as opposed to a generic object. Peek gives us a disk. Well, peek gives us a disk. Pop also gives us a disk. So if we wanted to modify this guy, let me,
That's cool.
before I do that, let's just modify this to use the built-in stack. So let me push these changes.
Cool.
All right, so they're up there. Now what we'll do is we will implement our game in terms of the built-in stack. So I'm actually going to have, ooh, can I extend it? Oh, so this is going to be, can I do this? Extends stack of disk. All right, looks like maybe. So I don't need this. I don't need num disks. Let's just start gutting this stuff. Just call upon our parents constructor. Don't need this. Don't need this. Remove disk is actually going to be this dot pop, which will pop a disk. So we'll call this disk D2R, just to remove. And then if D2R is equal to null, oh, actually we don't even need to worry about it. We can just do this. It already works the way ours works. So that's remove disk. Okay. Add disk is going to be a little bit tougher. So we'll say if this dot size, which is the number of elements in it, is equal to 0. There's nothing in the stack currently. We'll say this dot push D and return true. Otherwise, if we're allowed to push it, then we will do this. We could actually make that an OR, but let's just modify our code. Well, let's make it an OR. So if either the size is 0 or we're allowed to add it, push it. So that's add disk. Is there a... see what that looks like. Okay, so we're no longer getting the number of disks. Now we're just getting size. That was given to us by the... Is that it? Oh, it doesn't display it very nicely, does it? I guess it sort of kind of does.
Yeah, just gives
It's
you-
not a horrible representation. We'd have to rewrite the string method, the toString method, to make it look a little nicer, but this is legit. So source is going to be 0, destination will be 2, 0, 1, 2, 1, 0, 2, 1, 0, 1, 2, 0, 2.
So what's built in that's showing the memory address?
There are two. the two-string method. So here in tower, we've implemented tower in terms of a stack of disks. So we actually inherited from stack of disks, well, we inherited from stack of disks our tower. So our tower is a stack. Specifically, it's a stack of disks. So we get all of the stack, built-in stack data structures stuff. So we have push, we have pop, we have size, which is the count. So it's doing all the stack crap for us behind the scenes. We don't have to worry about top or anything. When we build a tower, we're just going to build a generic stack. So that's what we call our super constructor there. Remove disk is just going to pop. Even though we didn't write pop, we got pop from our parent, right? Add disks, this says if we're allowed to add it, so if the size of the stack is either 0 or the guy at the top of the stack, the guy we're trying to add is smaller than the guy at the top of the stack, then we're allowed to add it. So we are using the built-in stack data types peak. Then we're using the built-in stacks data method for push. Return true. So it's this method. So when I say this dot, or just say system.println, this guy is an instance of stack. And this is actually calling this dot toString. That's what's getting called.
Setup disk, is that where we set up our own two-string?
We could. Well, no. This is an instance of tower. So the toString method we got is the one we inherited from the stack data structure.
Okay.
And he's the one that makes it look like what the output there was.
But didn't we create our own two-string thing in the setup?
Set of disk? I don't think so.
Yeah, we messed around with that.
But it's still set to the super.
Oh, because of that. Oh, it is showing it. That's where it came from.
Yeah.
So really, we just want to return that, just that size. Now we should be in business.
There we go.
Actually, probably a little easier to read our game now because it all fits on one screen. But it actually shows it kind of backwards because this 1 is actually above the 2 is actually above the 3.
Yeah.
Well, I mean, that'd be right.
It doesn't really matter. You just have
Well,
to understand
If you
it.
think about it.
The top of our stack is a 1 right now.
Yeah.
Stop.
You just have to, yeah.
You just have to read it right to left,
Yeah, but
as opposed to having it turned on its
like if it was turned this way, it'd be fine.
turn who?
If you turned it.
Turned it on its side like that.
Side.
Yeah.
So could you
Then you
push
can
that
move just one.
Huh?
to GitHub,
That makes sense.
Well, no. This is my code.
please?
Just gotta turn the laptop sideways to play the game.
All right. But maybe the thing to notice here was this really that much easier?
No.
It's not that much easier, but it is cleaner.
Looks clean.
Well, all the same crap is happening.
Yeah.
All the same crap is happening. So, but you're allowed to use this now because now you know what push, pop, and peek do. Does that make sense? But notice as I wrote this, I had to look at pop and push and make sure they were giving me values that were reasonable, that were compatible with what I had before. All right. So. Built-in stack of disk data type. Right here, class, let's say. All right, so that one's up there.
I thought you'd written scripts to do that.
I did. I remember a few minutes ago I said I was going to write a script. Just the script's in a different directory, so I can go grab it if I wanted to, but whatever. It only takes 2 seconds. All right, questions about that? All right, so now we have fully working towers of Hanoi. Let's look at create a new Java project. CSC300 Spring 2015 Q. This won't take real long. Go ahead.
You had talked about a different type of for loop. Can you show that?
Ah, yes, thank you. It's just no pleasing you people.
Hey, you said you were going to do
except right now I've taken out my code that used it. Oh no, here it is. Here it is in my show. So in show, right now I'm going through bucket 0 to towers.length, I++. What I'm going to do here, actually, we'll lose the ability to have our index here, but that's fine. I'm going to replace that part of the for loop with what's roughly equivalent. That is for tower T in this dot the towers. In is Objective-C. That's Java. So towers T in this dot tower. So each time through the loop, T will be equal to the next tower in the loop. So the first time it'll be the tower at bucket 0, then it'll be tower at bucket 1, then it'll be the tower at bucket 2. All right, so I'll lose my ability to do my index here, so I'd actually have to say, int pos is equal to 0. Do something like that. And then, so instead of saying this dot towers at bucket I dot display, now I'll just say T dot display. Make sense? So this is a for each loop. It goes through and this is for each tower T in the array of towers. This also works for linked lists. The built-in linked list data type. I think it also works in stacks.
So it automatically knows to break down the loop once it reaches the goal?
Well, it's not actually removing them from the loop. What it does is it creates something called an iterator over this, in this case, an array. So for this array, it looks and says, oh, there's 3 things in here. So it essentially writes that for loop that we originally had written. Go to bucket 0, bucket 1, bucket 2. And each time through, it goes ahead and sets a variable named T equal to the tower at that bucket. And then we can work with T. So this is beneficial when we don't actually need the index. In this case, we sort of kind of needed the index. So we could say this is index 0, this is index 1, this is index 2. But functionally, this will do the exact same thing it did before. We just accomplished it with a for each loop. Make sense? It's kind of like I have to finish the game. Huh?
What happens now if we're doing
Illegal move. So illegal move would be
It just won't do
2
anything?
to 1.
No. Illegal move is
3 to or 0 to 1.
0 to 1. So illegal move.
Okay, so we kept that.
Yeah, I mean, nothing changed with how our logic. We just used the built-in stack data structure to hold our disks instead of our version of a stack. A disk is still a disk.
One more push to GitHub.
What with this?
Yeah.
All right.
You're slow as me, and I got 100.
Okay. All right. So we're starting to create another project here. And we'll go ahead and create our driver.
My bad, I started that.
You know what yawning is?
Like lack of oxygen. I know, that's why I'm so slow. This is what happens when you guys get old. You're going to be as slow as this. It's terrible. All right.
Already, I'm screwed. Slower even.
So now we're looking at the queue data structure. All right. So a linked list is a generic data structure. Okay. It's a generic data structure that supports adding to the front, adding to the end, adding to the middle, removing from all those places. So a linked list is a malleable data structure that we can use for all sorts of problems. Okay. Now a queue, like a stack, is very specific. So stack supported 3 functions, right? It supported push, pop, and peek. A queue supports NQ and DQ. DQ, get it? Haha.
People aren't getting your jokes today.
What's up?
People aren't getting your jokes today. Or they just not get it.
No, I typed something else in there.
I got it.
Oh, you got it now? What, the DQ or the D2F?
The D2F, but like, what was DQ?
DQ, I wrote that.
He was just there.
I thought it was just like something different.
Oh. So you looked up D2F?
No.
Oh, you still don't get it?
Oh, I get it.
Oh, you do get it?
Now I do, yeah.
Oh.
Down.
Oh, somebody told me.
Yeah.
Oh. No, no. You said down? No, you still don't get it.
Well, there's many ways you could have taken it. Though.
No, there's only one way to take this.
You've seen that show.
Whoa. All right. So a queue is a line, like a line at McDonald's. All right. NQ means get in the back of the line. DQ means leave the front of the line. So this is a first in, first out structure, as opposed to a last in, first out for the stack. So FIFO, first in, first out. LIFO, last in, first out.
Covering this stuff in accounting
Huh? Really?
right now. FIFO and LIFO.
Oh, see, good.
Yeah, my brother saw LIFO because he's an accounting minor and wondered what we were looking
Oh, did you tell him he wouldn't understand because he's too dumb?
at. Something along those lines.
Makes sense. Does your brother play football too? Does
He
he
had
play?
4 herniated discs in his back. He was forced to stop
Oh, so would you guys play the same position?
for a time.
So nobody knew who was coming at him. It's like, I thought we broke his arm. Bionic man. All right.
They made another one.
They made another one. We're mass producing Concordia. All right, so that's a queue data structure. It's going to support an NQ and a DQ. It is a FIFO.
That is a variable.
Okay, make sense? What a queue is? So for your homework,
I'm just going to start using DDAF for all my variables now. Especially anything with height, distance.
here, we'll come in and add it here in a second. I'm going to go ahead and I'm going to create a class in here called person. Okay, and a person is going to have a private string name. Actually, name's fine. Private double wallet balance. That's good enough for right now.
Start getting into accounting stuff. I will say okay.
Actually, let's just make this an int wallet balance for right now, just to keep it a whole number. All right, and we'll have a constructor, public person.
That's reasonable though. 'Cause I mean, who keeps changing their wallet?
That's right. And we'll say this dot name is equal to whatever name was passed in, and then we'll say random. Actually, let's do another. Yeah. We'll use that next time for doing our Actually, I'm lying. I'm going to make this more efficient. We're going to say private static random r is equal to do random. So now we need to import java.util. So this instance of random, well, this instance of random is actually a static field as opposed to an instance field. So this guy is owned by the class, not by each individual instance of the class. That way I only create random once and can use it multiple times. So how do I access this variable right here? How do I create a random number using that variable?
What's the name of the class? Person.r.
Yep. So this dot wallet balance is equal to person dot r dot next int, and we're going to say this person has between $0 and $10 on him. Make sense? So the efficiency of this is now I don't have to create a brand new instance of random every single time we have our constructor. I create it once, it's owned by the person class, and now whenever I need it, I just call upon it. So there's only ever one instance of random called R across all persons. If I create 1,000 people, 1,000 person objects, there's still only one instance of random called R. Make sense? All right. So this is how we'll build a person. And just as a quick example, we'll say person P is equal to new person Mike. Actually, let's just say person 1. This will kind of mimic what I want you to do for your homework. Person P2 is equal to a new person, person 2. And then we're going to create a quick display method. And this will say system.out.println. Hi, my name is this dot name, and I have this dot wallet balance on me. Don't mug me, please. All right, so when a person calls this display method, it says, hi, my name is whatever, and I have, this is how much money I have on me. And since we're randomly generate the wallet, I should be able to say p.display and p2.display. Hi, my name is person 1, I have $4 on me. Hi, my name is person 2, I have $5 on me. Okay? So your homework assignment is going to be to create a queue of persons. Fill it up with random people, and then dequeue all of them until the queue is empty, printing out their, calling their display method for each one. Now I'll go ahead and I'll go on to here. I'll create a new repository. CSC300 queue. All right, I'll steal this here real quick. So then I need to go to show in System Explorer, Terminal, CD, this, get init, get add star dot Java, get remote add origin this, get status is that, get commit dash m initial commit, and then get push origin master. So now that guy should be up there. There's our code. All right, so for your homework, I'll give you this as a starting point. Now, notice I've only explained to you what a queue is. I haven't shown you any queue code. But you know what a linked list is, and you've written a stack, and a queue is a lot like a stack, where it's a simplified linked list. You only have to write two methods, enqueue and dequeue. And we need more assignments in here.
Yeah.
Shenanigans.
What class is this? 9? We have 9 assignments.
Yeah. All right, so implement a queue data structure in terms of enqueue and dequeue. And use it to store 100 random person objects. Use it to enqueue 100 random person objects, and then dequeue those objects and call their display method.
So what does that mean? Does that mean we're supposed to generate 100?
Generate 100 persons,
And then
add them to the queue by enqueuing them, put them in line. So now you're going to have a line of 100 people.
does that have to be in order? Or,
Well, yeah, just
It'll be
put 100 people in there.
okay.
You're testing the use of, you're testing your queue. And then dequeue them.
Is this all in the person class then? Yeah.
Well, no, the person is the type of object you're storing. You're going to have to write a queue class. You write a queue class, and that queue is going to be capable of storing persons. Our Towers of Hanoi tower was capable of storing disks. Our original stack data structure was capable of holding ints. Make sense? So this is going to be a queue capable of holding person objects. All right, make sense what I'm asking you to do?
And then what's it supposed to end up doing with the call?
DQ them, take them all out. Once you put them all into the queue, bring them out of line one at a time, and call that guy's display method.
Okay, so it's just gonna display 100.
Display 100. You know, hi, my name is person 1. Hi, my name is person 2. Hi, my name is person 3. If you get where I'm going with that. So when you create your 100, just make a loop. Person I, person I, person I, person I. Okay? And this will be due midnight tonight.
Yes, good jokes.
All right. And if you want, as I'm walking down to the cafeteria, I can tell you about D2F, if you'd like. Okay.
Like the floor?